Hi folks, Astronomy Live. At last it's time to release SatTraker, my satellite tracking software which automatically tracks satellites based on their orbits and guides based on video. So basically the way this works is you have a video viewfinder on top of the telescope. What I use is a Samsung SDC 435. They now sell it as, I believe, the SCB 2000. It's a pretty affordable security camera, pretty basic, and a 50mm C-mount lens, which is then mounted to the rail on top of the telescope. You could also use a guide scope and any webcam-based imager, something like that, to achieve the same effect. Basically, what you do then is you start tracking using the orbital elements of the satellite, and then simply click on the satellite in the view to automatically start guiding on it and center it up in the main telescope view. So first step to operating this program is going to be to select the orbital elements. Now, unfortunately, the capture software I'm using right now doesn't show it, but there's a bar up here at the top with various menu options: File, Telescope Type, Tracking Type, and Image Orientation. What you want to do is you want to go to File and then select TLE File and click on that. Then pick the file containing the orbital elements of the satellite you want to track. At the moment, the program doesn't have any functionality for picking a satellite out of a file containing multiple satellites, so you'll need to make sure that the satellite you want to track is listed at the top of the file. It's okay if there's other satellites listed later on in the file, but the program will not read those orbital elements. It'll only read the orbital elements of the satellite listed up at the top. So you may just want to copy off the orbital elements in the 3-line format and save it in a text file for that particular satellite that you want to track that evening. It will only take orbital elements that are in the 3-line format with the name and 2 lines containing the orbital elements in the typical TLE format for this program. So then you want to make sure you've got the right telescope type selected. At the moment there are 2 options: LX200 Classic Alt-Az and ASCOM Alt-Az. There will be support later on for equatorial mounted telescopes, but I wanted to get this initial version out for testing and see if it works. Hopefully there's a viewer out there that has an ASCOM compatible telescope mounted in an altitude azimuth configuration that can use the move axis method. Now, the program will assess whether the telescope is capable of using the move axis method with ASCOM when it first connects to it. If it's not, it will automatically disconnect from it and not allow you to attempt to track anything because it is entirely dependent on that functionality. The LX200 Classic, for example, does have an ASCOM driver set, but that driver set is not compatible with that method, and so it will not work. For other telescopes, though, it should work. I believe that many Celestron telescopes do work with that method as long as the hand controller is version 1.6 or later for NexStar telescopes, but I'm not 100% certain about that as I don't have a Celestron telescope to test it with. But by all means, give it a try. If it connects properly and it doesn't reject you for having an incompatible telescope, then it should work. But, again, this hasn't been tested with any ASCOM compatible hardware, and so it's entirely experimental at this point, and please use it at your own risk and be careful. If you need to, be ready to stop the telescope if it starts driving in an undesirable way or at a higher rate of speed than it should be moving. So be cautious, especially when first using this program, because I can't be completely certain of how it will really behave. There could be hidden bugs or problems there in the code. I haven't been able to test it with ASCOM at all. So just keep that in mind. But if there are any bugs or problems with it, I'll be working diligently to fix those as quickly as possible and update the source code on GitHub. The link to the source code is also in the video description. It will be on GitHub, and that's where you'll find it. Once we've got a stable version working and tested and verified, then I will be releasing executable versions for those who don't want to go through the process of installing Python and all the dependencies. I've got a video tutorial on how to install Python and some of the important dependencies that this program functions on that I will also link to in the video description. There's also additional dependencies that this program uses that I wasn't aware of at the time when I made that tutorial, but I'll also list those in the description, and they should all be simple pip installs. Once you've gone through the tutorial, you'll know what that is. So once you've got the telescope type selected, then you want to select the tracking type. There are two options: feature tracking or brightness tracking. Now, in general, for most satellite tracking, brightness tracking will be your best bet. It's simple brightness tracking based on the brightness of the object. What you've got here, you've got this blue box that follows the cursor around, and this is your region of interest for tracking. You can change the size of the blue box using the scroll wheel with the mouse. You want to find the satellite in the view once you've started tracking, which I'll show you how to do in a moment. But once you've started tracking, you want to find the satellite in the view and then click near it with the blue box. You don't want to click directly on it. So if these lights here were the satellite, you wouldn't want to click directly on them. You actually want to click a little off from them. Any direction, it doesn't matter, as long as it's still in the box. But you want to actually be clicking on the background, because what you're going to be telling the program by clicking there is this is the background intensity. And what it will do is it will then look for the brightest pixel in that blue box and automatically scale the threshold for detection based on the background intensity that you clicked on. It will set the threshold cutoff as the median value between the background that you've clicked on and the brightest pixel in the image in that blue box. So if I click a little away from those lights, it automatically scales to cut out any camera noise and tracks the lights properly. So this is computationally the fastest way to do the tracking. It's not as complex as feature-based tracking, but feature-based tracking is good for more complex tracking objects. And this may become more important later on in the next module that I plan to release, which I've titled Ufo Tracker. And really, it's for just anything you happen to see flying around in the sky that you want to track, such as a rocket launch, for example. You may be wanting to track a rocket launch which is quite bright, but then the contrail behind the rocket might also be whiting out the camera as well, and you don't want it to migrate the tracking box down that contrail. You want it to stay at the tip of the rocket. Feature-based tracking is good for that because it will actually learn what the feature is that you're trying to track and keep up with that. So it's more computationally demanding, and it also will simply try to hold the feature wherever you've clicked it. You notice when I click near the satellite, if this were a satellite, it automatically centers the box over the brightest object that it finds. Feature-based tracking doesn't work that way. It will simply maintain the tracking box wherever you've clicked it. So if I do feature-based tracking and click just off to the side, it will hold the image just off to the side. For feature-based tracking, you do want to click directly on whatever it is that you're trying to track, and so clicking accuracy becomes important, which is why it may not be as ideal for satellite tracking, but it is necessary in some cases that will become important later. It's also useful for tracking stationary objects, which will become important in a moment when I describe the camera calibration procedure. So the next thing you want to do is center up the telescope on a distant object. Could be any object, could be a star that you're tracking, and get it centered in the view, and then set where the center of the telescope view is in the viewfinder camera. And you do that by clicking Set Center Point. So you click Set Center Point, and then click wherever it is that the telescope is actually pointed. So if you're pointing at a bright star right about here, you click that, and that sets the center point. The red box moves there, and that tells the program where the main telescope is pointed, and that is the point where it will move the satellite to once you've started tracking it. So once you've started tracking based on the orbit, and then you click on the satellite, it will then move the green box to the red box as best it can. Now, the other thing is that when you've clicked Set Center Point, that's a one-time command. It will move the red box wherever you click next, and from that point on, after that point, it reverts to its original behavior of setting the target, whatever it is you're trying to target, for tracking. You can also move the red box 1 pixel at a time using the arrow keys on the keyboard. So this is handy in the middle of tracking if you're trying to adjust where the telescope is pointing. If you're trying to adjust where it's putting the satellite in the main telescope view on the fly, you can do that with the arrow keys, moving the tracking box 1 pixel at a time for fine control. So now you need to calibrate the camera. The program needs to know what the image scale is. It needs to know how many degrees of sky correspond to each pixel in the view. Fortunately, this is an automatic procedure. So what you want to do is probably select feature tracking, because this is something that you can actually do during the day before you're ready to track satellites. When you're getting ready, set up your telescope during the day and point at a distant object like a tree or a power pole, something that you can center up on with the main telescope view. And you can actually set the center point at that stage as well, as long as you can be sure that the guide rings aren't going to shift at all, or that the viewfinder camera is going to be pointed in the exact same direction at night. The other thing that you can do is camera calibration, and this is best to do on a stationary object, so it is best to do this during the day. And for that, feature tracking is probably your best bet, because here it doesn't matter if the object is bright or dark or what. As long as it's a distinctive feature, you can track it. So with feature tracking, as I said, it will hold the object exactly wherever you've clicked. It won't try to center that object up. But for camera calibration, it doesn't matter. It just needs to be able to see where a stationary object is so that it can lock on to it. Then when you click camera calibration, it will automatically start moving the telescope in one direction for 100 pixels. And then it will stop the telescope and assess how far it moved in terms of degrees, what the encoders are reporting. It will then calculate what the actual image scale is based on how far the telescope moved to achieve 100 pixels of displacement. If the tracking target is below the center of the view, it will automatically try to move the telescope to position it higher in the view. If the tracking target is above the center of the view, it'll automatically move the telescope down to towards the center of the view. Now, this of course only works if it knows what the image orientation is. So you need to make sure that the image orientation is set correctly. The options for the image orientation menu up at the top are normal orientation, vertical flip, horizontal flip, vertical and horizontal flip. So if you're looking through a refractor, some sort of guide scope, the image orientation may not be normal. And if your camera doesn't have the ability to change that within the camera internally, not a problem. The software can do that for you with the image orientation selection. You just need to make sure that whatever you've selected has returned the image to a normal orientation, vertical and horizontal, orthogonal to the view. So once you've calibrated the camera, you've set the center point, and you've selected the orbital elements file and connected to your telescope, if the camera's started, you're ready to go. All you have to do is click Start Tracking the Satellite, and then it will begin tracking based on the orbit. It should show up as a stationary object while the stars are trailing in the background as it rises over the trees or the horizon. Once you see the satellite in the view, all you have to do is, again, if you're using brightness tracking, click slightly away from the satellite to set the background intensity, and it will automatically find the brightest pixel in the blue region of interest tracking box and start centering it up. Now, if a background star is sufficiently bright and happens to pass through the view, it may confuse the software for a moment. It may even accidentally lock on to the background star. If that happens and you need to reset the tracking at any point, all you have to do is right-click to undesignate the tracking box. The program, if it is currently tracking a satellite, will then revert to tracking based on the orbit only and attempt to minimize the error relative to the predicted position based on the orbit alone. Then you can redesignate the target by clicking with the blue box again where you see the satellite in the view. Pretty simple and pretty effective. So I've been able to track a variety of satellites at this point, including the Hubble Space Telescope and the International Space Station. For the International Space Station, the pass was not ideal. It was actually during the day, and the sun was well above the horizon at that point. And I was just using my usual viewfinder camera, which had a simple 50mm security camera lens mounted on the front. And this turned out to not really be ideal for that situation because the blue sky was too bright and ISS was only visible near the peak of the pass, so I didn't get much time on it. Normally, if you have a nice long pass of the satellite, once you've set the software to start tracking, you're pretty much hands-free at that point. I found that it's pretty rare for a sufficiently bright star to confuse the software, so you can pretty much go over to the telescope and do whatever it is you need to do once tracking is set up and running. So you can adjust the focus, fine-tune it, make sure the view is at its best possible quality at that point, which is quite handy. But in this case, there just wasn't enough time. The station wasn't visible in the viewfinder until just moments before it reached its highest in the pass, highest peak of the pass, and at that point, that was as far as I could track it. So the view there wasn't as good as it could have been. The telescope was a little bit out of focus due to mirror flop. As the telescope pitches up my Schmidt-Cassegrain, the mirror can actually shift in its position, and that's how the telescope normally focuses its view. But due to gravity, as that telescope pitches up, it can cause the mirror to flop back a little bit, and this causes the image to become a little unfocused. And unfortunately, there just wasn't enough time to correct that. But one thing I am doing to correct some of these videos is I'm also cooking up another program, which is based on the same brightness tracking algorithm, but what you can do is pass your video through it once you've recorded it, and it will align the images based on brightness and then stack them in a rolling average. So it will use a rolling average of 10 frames to basically do a miniature stack on each video frame, where each video frame corresponds to that rolling average of 10 frames. Now, as your perspective of a satellite changes as it passes overhead, that can actually blur the view if you try stacking images that are too far apart, which is why it only uses a 10-frame rolling average. It's not like planets where you can stack hundreds and hundreds of frames to produce a nice, clean image. You can't get away with that with satellite tracking, but you can get away with fractions of a second. So if you're running 30 frames per second recording video, or even higher, you can definitely get away with a 10-frame rolling average stack, and that will improve the quality of the view. It also stabilizes the footage, so if you're running it at very high magnification, it can dance around in the main camera view a bit as it tries to hold it steady, but with a little bit of image stabilization, you can take that right out and get really good looking video of various satellites like Hubble and the space station. So stay tuned for what that looks like, and I'll be releasing that as well. Once we've got a stable version here where it's been tested with ASCOM and everything else, I will be releasing an executable version of this program so that you won't need to install Python and all these dependencies to get it to work. It'll work right out of the box as a simple executable file. But before we get to that step, I want it to be tested with ASCOM telescopes to make sure that it works and that we've got the basic bugs worked out and the basic functionality and features in place and operational. Alright, so let's take a look at some footage recorded with this software. So here's stabilized footage of the Hubble Space Telescope recorded by the software. As I adjust the exposure on the top of the camera, it shakes it and produces this weird electric-looking effect. It's actually streaking around the view because I'm shaking the camera as I'm adjusting it, but because it's stabilized, it centers all of those streaks into the center of the frame, producing that electrical-looking effect. Then, as Hubble begins to rise higher and higher, its slant range to the telescope decreases, and gradually it goes from being a point of light to an elongated shape, revealing the actual length of Hubble's optical tube assembly. This is not the first morning that I had tracked Hubble with the software. In fact, you can see some earlier footage on the channel as well. And if you look, you'll notice that the apparent orientation of Hubble in that footage is very similar to what you're seeing here, and indeed, it looked quite similar throughout all the mornings that I've tracked it since the software became operational. Unfortunately, that's because Hubble is currently not operational. It's currently being diagnosed by NASA after a gyroscope failed. They tried to bring a backup gyroscope online to restore it to a 3-gyroscope operational mode, but that new gyro began reporting wrong values for Hubble's rotation. So NASA's currently looking into it, but they may have to resort to going to a single gyroscope mode to prolong the life of Hubble. Although it appears to be rotating here, that's actually due to field rotation, because the telescope is not aligned parallel to the axis perpendicular to the plane of Hubble's orbit. Here's the International Space Station, which I recorded on Sunday morning, over an hour after sunrise. Unfortunately, because of that fact, the viewfinder camera had a very difficult job trying to detect the space station against the blue skies, and it only sporadically detected it, and only near the peak of the pass. As a result, the footage was not nearly as long or as stable as the tracking footage I got of Hubble and other satellites, so I'll have to wait for a nighttime pass to get the ideal results. Because of the short period over which I tracked Hubble, I didn't have time to go to the telescope and fine-tune the focus. The footage you're seeing has actually been slowed down significantly. With all of that said, I credit this software for being able to get footage at all that late into the morning under those conditions. Had I been manually correcting the tracking the way I would have done with older software that I've used, it would have been difficult, if not impossible, to get any frames of the space station. The viewfinder camera that I was using was not ideal for that situation, and it could only see it near the very peak of the pass, where only a few seconds were available for tracking. Lastly, here's a recording of the video viewfinder as it was tracking the Hubble Space Telescope. As you can see, as soon as I click on Hubble, it brings it to the red box where the main camera can record it through the telescope. The tracking was quite stable throughout, even though it reached 71 degrees over the horizon and was traveling quite fast. At that point, it hit the north side of the meridian, which is where there's a hard-coded stop with the LX200 that forces the telescope to swing around 360 degrees to the other side in order to untangle its cords. Nevertheless, the software did a fantastic job tracking it to that point, and it will provide good tracking for any low Earth orbit satellite as long as it's bright enough to be seen by your video viewfinder. Thanks for watching. You'll find the source code in the video description. Clear skies, folks.